Welcome to Limits Day 2 Analytical Approach. Let's actually do some work instead of just putting numbers in a calculator and using a table. So let's get right at it. I'll let you read this. Why is it that mathematicians always do that, or even the math teachers? They show you the hard way to do something, and then you spend blood, sweat, and tears to work on it that way, and then they turn around the next day and show you the easy way. I think it's so that you appreciate the easy way a little bit more. So replace this x with this x right here with a 3, and it looks like the limit is just going to be 5/3. Okay, replace this x with a 0. So x 0 squared, replace that with a 0. It looks like to me that that limit will be 4. Now, of course, with some limits, it's not going to go that easy, and we'll have to do some, what I like to call, algebraic shenanigans to get to the point where we have a function that is defined. Sometimes when we replace, we get zeros in the denominator. Alright, the limit as x approaches 4 of x squared minus 16 all over x plus 4. When we replace with a 4 squared and 4, we end up with 0 over 0 when we replace. Not cool when we replace with a 4. So then what we want to do instead is to see if we can simplify that expression at all before we replace. And it's fairly obvious in this scenario that you can factor the numerator, because it's the difference of two squares, into x plus 4 and x minus 4. Those x minus 4s will cancel out. Now let's go ahead and try to replace again. Replace the x with a 4. 4 plus 4, 8 times 1 over 1. That limit will be 8. Mind you, if we actually put a 4 in there, it would be undefined. But we're talking about a limit, how close it gets. It never really gets to 4, just gets really close. Alright, let's try another one where when we replace, it ends up yielding something that's not cool. Alright, when we replace with 1, we get 3 minus 4 plus 1 all over 1 minus 1, 0 over 0. So let's see if there's any way we can simplify or factor. 3x and x in the numerator. Second sign is positive. That means these two signs are both the same. First sign is negative. That means both of these have to be negative. And factors of 1, 1 and 1. That yields us negative 1x and negative 3x. Hey, that's a good job factoring. In the denominator, x plus 1 times x minus 1. The x minus 1s will cancel out, and we have a new limit. The limit as x approaches 1. So now go ahead and replace x with a 1. 3 minus 1 all over 1 plus 1. 2 over 2. The limit is 1. Alright, just glad we don't have to use a table to figure that out. Next, please. Alright. When we replace, we get the square root of 25 minus 5 all over 25 minus 5, 0 over 0. So let's look at this and think of this as the difference of two squares. I know this isn't a square, but we're going to try to think of it that way because we want to try to see if we can mess around with this. Okay, if this is a perfect square, what do you multiply by to get x? Well, that would be root x. So root x minus 5 times root x plus 5. When you multiply those out, you get x plus 5 root x minus 5 root x minus 25. These middle terms will cancel out and you're left with x minus 25. So it does actually work. Okay, I'm going to back up my writing a little bit. Just a little bit there. That's in the denominator. In the numerator we have root x minus 5. The root x minus 5s will cancel. We'll put a 1 in the numerator because when you cancel you're supposed to replace with 1s or any other factor that works properly. So now let's try to replace one more time. 1 over the square root of 25 plus 5. Square root of 25 is 5. 1 over 5 plus 5. The limit is going to be 1/10. I told you, algebraic shenanigans. No other way to describe it. Alright, here is the next limit. First, let's go ahead and replace each instance of a 6. Sorry, each instance of an x with a 6. So you got root 6 minus root 6 all over 6 minus 6, 0 over 0. Alright, let's see if we can somehow algebraically manipulate this function and see if we can come up with something. Okay, just like the last screen, think of this as the difference of two squares. Square root of x is root x. So this can be factored into root x plus root 6 times root x minus root 6. In the denominator, and then in the numerator, root x minus root 6. We'll put that in parentheses just to make it a little bit easier to cancel. We'll cancel that, put a 1. We'll cancel that, put a 1. And now it's limit as x approaches 6. Let's go ahead and replace again. You got 1 over root 6 plus root 6, 1 over 2 root 6. And yes, we finally arrived where we don't have to rationalize the denominator. You finally graduated into not having to rationalize the denominator. We'll just leave the answer like there. I don't really care if there's a root in the denominator any longer. Isn't that fairly cool? I think it is. Okay, let's go ahead and move along and we'll try the next screen. Or as Harry Callahan would say, go ahead, punk. Make my day. Alright, limit as x approaches 3 of x minus 3 over the expression 1 over x minus 1 over 3. When we replace 3 over 3 all over 1/3 minus 1/3, 0 over 0. Arg. So let's see if we can manipulate this algebraically. First of all, I think we should probably try to get rid of fractions. So the least common multiple of x and 3 is 3x. So we're going to multiply this denominator by 3x, and we'll multiply the numerator times 3x. So in the numerator we'll have 3x times x minus 3, and in the denominator distribute that 3x. The x's cancel in the first term, and you've got 3. Distribute to the next term. The 3's will cancel, and you're left with x. Oh man, those two are really close to each other, but they kind of look like opposites because it's x minus 3 and 3 minus x, and actually it is opposites. So what we're going to do is factor out a negative 1 right here. So that would be negative 1 times 3x times negative x plus 3. And that certainly now does look like a lot like 3 minus x. We can cancel those out because they're the same thing. I just don't have them in the same order, but they're the same thing. So now we're really just looking at the limit as x approaches 3 of negative 3x. Looks like to me that the limit is negative 9. And it is negative 9. Oh, by the way, negative 9. Did you know that Beethoven wrote a whole symphony about his favorite number, negative 9? Guess which symphony it was? No, it wasn't the 9th symphony. It was the 5th symphony, because it starts out negative 9, negative 9, negative 9, negative 9, negative 9, negative 9. Oh boy. My wife, she's back there. You can't see her behind the curtain, but she's not happy with me. She thinks I'm weird. That's okay. I have to trust her judgment on it because, you know, she did marry me after all. And you know what? I'm an independent thinker and have my wife's permission to say so. Alright, here's our last limit. Let's go ahead and replace. 1 minus 7 plus 6 all over 1 minus 1, 0 over 0. So let's go ahead and try to change it algebraically. Always got to check first. Maybe the limit will just work the way it is. So what I'm going to let you do is I'm going to let you factor this synthetically. You know, 1, we're going to guess a 1, any factor of 6. And the coefficient of x cubed is 1. Coefficient of x squared is 0. Coefficient of x is negative 7. And the constant is 6. I'll let you go ahead and play with it to help factor. And then we'll come back. So pause, factor. Have fun. Alright, you bring down the 1. Multiply those two together. Put it right there. Add those together, put it down there, multiply those two together, put that multiplication there, add those two together, multiply the 1 times negative 6, add those together, you get 0. Hey, it factors. So that would be x minus 1, negative 1 right there, times x squared plus x minus 6. That's that trinomial factored. And then the denominator, x plus 1, x minus 1. Go ahead and pause this just to catch up. Then you can go ahead and cancel out the negative 1's, replace them with 1's. Then now go ahead and try the limit again. 1 plus 1 minus 6 all over 1 plus 1, negative 4 over 2. The limit is negative 2. Thank you, and have a great evening. This concludes Lesson 2 on Limits, Analyzing Approach.